Hello again. I know the last video is not so good, but I hope this video will be much more better. Today we will start new chapter 11. Before starting this chapter, I want to remind you that if you have any questions about the previous chapter, you can ask your question in our system as a forum and gently answer that question. If you understand any question in detail, maybe I can add new video, extra video to solutions of the questions. Additionally, I am planning to solve the questions in previously asked in the exams in different video. Therefore, please don't worry about that. If you don't understand the question, also what will be exam in real exam. Just I will help you about the exam questions. Okay, be patient and try to understand the theory of our principle, our course details. Okay. Now in chapter 11 is the design of beams. You remember the actual course, this chapter title is design of beams and shafts, but I said that the shafts design is mostly related to mechanical engineering course. Therefore, I want to focus on the design of beams. Actually, I'm not exactly show the design standards to design of beams, because it is the formulas of the design of beams from the standards is a little bit complicated and we deal with and have a detail. And if I want to spend time to design of beam, also it's extremely important to what material use for design of beam. For example, design of reinforced concrete standard is different, design of steel is different, if you want to design in aluminum material is different. Therefore, in our program, civil engineering program, design of structures given in extra course. For example, maybe you are now taking the steel structure courses, and therefore in that course you will learn the design of beams, of steel beams, in detail in that course. But now in that course I want to give a main information about what we focus on when we want to design the beam. Just only I want to give the basic idea to you. Okay, let's start to our design of beam. You remember we already know how we can calculate the stress of beam. So we know, for example, I want to think about like the beam and I put two external loads on the beam. So beam is deformed and stress occurred on the beam, and we want to categorize the stress as normal stress caused by the bending moment, like this. And I want to also take a cross section, infinitely small cross section, and we have a normal stress caused by the bending moment. Also, we have the shear stress by using this loading type caused by the shear force. And also, if have any axial load, I didn't show in the as an external, but if as any normal stress caused by the axial force, also we have to consider the axial force, the normal stress caused by the external force. These are the internal stresses occurred when we apply the external loads. So mostly that when we are designing on the beams, we mostly consider the normal stress caused by the bending moment, because the most effective case the design of beam is the bending moment. If you want to design a column, we are mostly considered the normal stress caused by the axial force, but for the beams, especially where the distance or the length of beam in span of beam is increases, also effectiveness of the bending moment also increases. Therefore, we are firstly focused on the normal stress of the caused of beams. Sometimes, especially short span, also shear stress can be much more critical than the normal stresses. Therefore, also we have to consider the shear stress when we are designing the beams. And in this chapter, I don't want to focus on the normal stress of the axial force. Also, I say that if you want to go in detail, you will take extra courses such as steel structures, reinforced structures. You will learn to all details of the designing standards and designing ways. Therefore, just I want to give the basic ideas. Therefore, I'm just only focusing on first of all normal stress, then I will check to the shear stress. How we can design them? First of all, after loading, we obtain internal forces. Normal stresses cause the bending moment. This stress, I want to call as a sigma maximum, and I mean the normal stress and the many normal stress occurred on the anywhere of the beam. First of all, I want to find the maximum normal stress. Then, and it's equal to the maximum moment occurred on the beam. First of all, I want to, after applying load, after I found to do maximum moment, then moment of inertia times c. You remember to the longest and the distance from the natural axis, I call that a c. This should be, to sigma maximum should be allowable stress. How we can obtain the allowable stress? This allowable stress is obtained from our material properties. Therefore, we cannot calculate the sigma allowance. So we will choose the material. We will look at our standards. For example, steel material. If allowance, for example, I want to say like 240 megapascal. And I look at the standards. I find the material property, and in material property they say that and sigma allowance in that material is 240 megapascal. Therefore, we are not go in detail how we can obtain the sigma allowance. It is mostly related to the structural material courses. Therefore, you can ask your instructors about how we can obtain the sigma allowance, sigma allowance stresses. Also, designing steel design or reinforced concrete structures. You can ask our instructors who give the steel structure courses and reinforced concrete structure courses. And also, I want to simplify with the moment of inertia divided by c. I call it as a section modulus. Section modulus is related to resistance to, and it is meaning that the resistance to the bending moment. So if our sections modulus is higher, our stress going to the lower. If our sections modulus is lower, our sigma values in internal stresses, normal stresses values becomes larger, bigger. Therefore, and how we can define the section modulus in how we can obtain the section modulus is the section modulus. You can see the moment of inertia, it's related to section properties. I mean the cross-section properties, moment of inertia we can find. Therefore, if we choose any section, and we can calculate directly the section modulus. For example, if I have already sections, section modulus available in the section list properties. Therefore, if which we change the section modulus in order to find the optimum section to our design for designing beams. So I want to continue. I'm sorry. Sometimes I have a little bit trouble to, yes, like this. Okay, so if I have a maximum moment divided by sigma levels, if we want to do, it's our variable is, I want to say, the section modulus. I want to make the ln the section modulus, therefore the section modulus should be maximum moment divided by sigma levels. This is the required sections. So our sections should have a section modulus that whose value is greater than the maximum moment divided by the sigma levels. Just are the banding check criteria. We choose our sections, relate these formulation like this. Therefore, our sections should be greater than section area. After that, for example, if I have many sections, and for example we have 20 sections and 15 sections satisfy these requirements, like S should be greater than section requirement, which section we will choose in order to make the most economically. Therefore we have choose the lightest, having a lightest weight in the steel structures, especially in the steel structures. The cost of the structures related to weight of the structure. Therefore we wanted to choose the lightest section, lightest weight sections. Who is the lightest weight? For built-up sections, we can also define, formulate the sigma requirement with respect to the formulation, and we can define the sections. So if after defining the sections, also we have to do, I say that we have to also check the shear stress. So how we can obtain shear stress? Maybe you remember that the shear stress, it's shear stress from unit 7. I remember that. So maximum is V maximum times Q area moment of inertia to moment of inertia times T. Mostly for I sections we have a shortcut formulation in order to simplify this formulation, because finding Q is much more complicated. Therefore it's very close to the, and we divide it by a web area. For I sections we can use a shortcut. For if we have a rectangular sections, also we can use 1.5 times V max divided by A. And in some questions we can use these formulations in order to simplify our calculations. These maximum should be to allowables. If our section does not satisfy these requirements, we have to update our chosen sections in order to satisfy these check. So I want to do also, it's a good thing that it's to practice an example is a good thing. I think it's like if we have a beam, this is, you can see the loading showing in here. This point is the pin support, this point is the roller support. Maybe you cannot see. Oh, sorry, just where is it? Yeah, this part is the pin support, this part is the roller support. Here is we have external loads available, and also allowable bending stress is given 170 megapascal. Also we have a two allowable shear stress also given. The question ask me that select two appropriate to optimum is the best W shape that will carry the loading shown in this figure. So we have how many sections? 1, 2, 3, 4, 5, 6. Also in as meaning that the section modulus and units is given to millimeter cube, but it's these values is multiplied by 1000. I don't have enough space, therefore I want to say the like as meaning that I mean the like 1,120,000 20,000 millimeter cube is, that's meaning that, okay, don't confuse first of all. Also other properties giving d means the depth, tw is the web thickness, and this is the area web of these sections, also total area of the sections. These properties taken from the standards, okay. So we have a like ready sections, and we want to choose the two most optimum section. So first of all, I want to start. Okay, most of you have a maybe trouble to find the maximum moment and maximum shear force. Maybe I can solve for you to it. Also, you remember you already learned these finding values from the static course, but I think I have time, therefore we can remind you to how can find. Do you know short way or not? But I want to draw moment and shear force diagrams by using the shortcut. First of all, I want to draw a free body diagram. I put line for beams. I want to do add and our point loads, its values I want to write 120, 60, and also I want to do reaction forces. I want to write like, I don't know, kind of sense. I want to say this A, and this point is like B, therefore I want to write like is AY, and this is the point B, and here is the like B, like AX. You know, all spaces is important for me, therefore where's my eraser? Sorry that I'm looking for my eraser. I cannot find. Where is it? Sorry. Where is it? My eraser. Okay, I found it. It's available in my whiteboard. Okay, I want to delete the point A and B like this. Okay, so we have three unknown. We have three functions. Sigma MA. I wanted to take the counterclockwise is positive is equal to 0, and I want to write, and this distance is from the sections I can see. I want to look at the previous slide. I think they're much better. 2 meter. This is 2, and this one is 2, and this one is 2. Okay, I wanted to go back to the next slide. Anyway, okay, sigma MA is equal to 0, and I take the counterclockwise. AX and AY don't make any moment to point A, therefore just we are starting from the 120 produced moment is negative moment, value is minus 120 times 2. Then B, it rotates to do again, I'm sorry, this one is the clockwise direction, because my B is produced the moment is counterclockwise, and therefore I put positive. That's B times 4. Okay, then the last one is minus 60 times as just 6. Again, this moment produced to negative moment is clockwise direction. This should be equal to 0. After that, I find to B is equal to 360 divided by 4. I think that should be like 250, just 360, 600, 150. I remember that. Let me check. Yeah. Like 150. So I want to continue. Sigma fx is equal to 0. If I write in here, there is no force available, therefore ay is equal to 0. And the last one, sigma fy is equal to 0. Not ay, I write like this, should be ax is 0. Ay plus ab, also I want to, this direction is positive, this direction is positive, also I have to write minus 120 minus 1 minus 60 is equal to 0. You can find ay is equal to 30. So we find to do reaction forces. So I want to erase these calculations and I want to locate the reaction force at the diagram, free body diagram, because I found the locations. I want to do relate to unknowns. X is equal to 0, therefore I don't want to write to the ax like this. I want to write for ay is 30 and I wanted to put 150 for b. So now we will start to the shortcut of our moment diagram, and I want to put some lines to help me to draw moment diagrams clearly. This is the shear force part. I want to do in positive in shear force, a negative like this direction. Okay, how we can draw this shear force diagram? Look at these values. It's 30 in its up direction. I put to the positive. Therefore, start from the 0. If I put to 30, this therefore initial we start from the 30. From this point to this point, there is no force available, external force available. Therefore, this should mean straight line between from A to this point. Therefore, 30 is not changes. Then I realize the force 120, but direction is down direction. Therefore, I already have the 30, but I have to subtract the 120. I obtain the minus 90. Therefore, I put to minus 90 in here. I don't want to write the minus in here. I'm sorry. This is like 90 in here. Okay. Then, from this point to this point, there is no external force applies. Therefore, 90 is continuous. 90 continue from this point to this point and point B, and on point B we have like forces 160, 150 in up direction. Therefore I apply the minus 90 plus 150. I obtain positive 60. Therefore I start from like I am going to do positive 60 like this, and again there is no force applying from this point to this point, and that should be, and that's done. After putting 60 in, we finished from the 0. It's also a checkpoint. Every time we start from the 0 and we have to finish with the 0. This is the shear force diagram. So after shear force diagram, I want also draw the moment diagram. Also, moment diagram is shortcut is very simple. You remember that an integral of the shear force is equal to the moment. Therefore, you remember that integration meaning that to area. Therefore, if we calculate the area, we also find two moment changes for this question. So, first of all, I wanted to calculate the area of the shear forces diagram, and I want to write this in first area. I want to write 1, this is 2, and this is 3. So area 1 is (30) times 2, it's equal to 60. Second area is A2 is minus 90 times 2 is equal to minus 180. And third area is A3, I think you can see, and 60 times 2 is equal to 120. Now I want to start the drawing to the moment diagram. And like shear force diagram, we will start with 0. In this moment diagram, there is no extra moment available on free body diagram. Therefore, I will just only add the areas shear force, the moment changes due to the shear force, and I start from the 0. I add to 60 from this point to this point. Therefore, from start 0. I forgot to say, and this is the up direction, I put the negative, down direction I put the positive. Therefore, this is the positive 60. I start from 0 to 60, like this. Then after, from these region, the moment changes is minus 180. Therefore, if I add to the 60 minus 180, I obtain the 120. Therefore, I put the straight line between the from 60 to 120, like this. Third line is the A3 is the 120 positive. If I add to the minus 120, I obtain 0. Also, that's the proof that my calculations are correct. If I not obtain 0 at the end of our calculations, we made some mistakes to calculation or areas or some kind of please, we have to go back to check our calculations. These are our moment and shear force diagram. You can see the maximum absolute moment is the 120. Don't worry about the minus, because you know the positive meaning that positive moment meaning that like that direction, and negative moment meaning that like this direction. But in both effects we have same magnitude of moment. Therefore, we have to consider the absolute maximum moment. Additionally, is also maximum shear stress. You should see the minus 90, but we don't consider about the minus. We are also consider to absolute moment shear stress. Therefore, we will take to do. We will take to do to Vmax is 90. Maximum moment is 120. Okay, so first of all, I said we will consider to do bending. We have to check our. We will choose our the optimum shape by taking in the account to the bending moment, normal stress due to the bending moment. For this, we remember that first of all we try to calculate the required section modulus. we already know the maximum moment. I want to do work with Newton and moment in order to calculate Newton millimeter. Newton divided by millimeter means like the megapascal, therefore I have to convert all the units to Newton and millimeter. And 120 kilonewton meter I multiply by 10 to the power 6 to convert to Newton millimeter, and divided by 120, and I obtain this sectional requirement is 705 10 to the power 3 millimeter cube. So if we look at the sections, we can see all the sections are greater than the section required. In other words, we can choose any section in this table I want, but I remember that I said to find the optimum section. Due to economically, we choose the lightest sections. How we can find? We will choose this one? No, because the weight we consider the weight, and which property related to weight is area. Section area is related to weight. You remember to weight is equal to length times A times rho, and so length is constant, we eliminate the length. Also rho is our material is homogeneous, therefore rho is constant. Also weight is proportional to area. If we choose the lowest cross-sectional area, we will choose the lowest weight. Therefore I'm checking, and this section is the lightest section, therefore I want to erase. I don't draw clearly, and I want to erase this part and this part. This section is the best section for check normal stress due to bending. So sorry, let's change. Sorry, something happened to do. Yeah, sorry that. Where is it? Yes, and find it, and this section. So again, then we will check to the shear stress. You remember in shear stress we have a shortcut formulation for I-beams. Where is it? I pass this too quickly. In bending check and shear check, where is it? Yeah, shear check we have a shortcut is the area web is the sorry, for I section we have a shortcut is V divided by area web. I want to apply this formulation. Just to the total shear stress is 90. Remember that I multiply 1000. Therefore, in order to convert to the kilonewton to Newton, I divide it by the area web. Also area web is given in here. Also if I divide it by the 90,000 divided by here, we obtain to maximum. Also we compare with our allowable shear stress. We can see our to maximum is lower than to allowable shear stress. Therefore our sections also satisfy shear check requirement. One more example. This is now in this example we will not use the radius action. We have to find two section dimensions which respect to the section with respect to the stress check. Okay, we have a laminated wooden beam shown in this figure. Loading also shown in here. There is also just okay, easy to see. Laminated wooden beam shown in this figure supports to the uniform distributed load. Also, I want to say these connections are pinned. Okay, like this. And also, if the beam has the height width ratio is 1.5, so if we choose the width of the beam, for example, we don't know the value of, I say the A, height should be 1.5 A. So also allowable bending stress is given 9 megapascal, allowable shear stress is given 0.6 megapascal. So they're finding to what is the value of L, what is the minimum value of the A, to smallest width is the A to resist both shear and bending stresses. Okay, first of all I want to draw the moment and shear force diagrams. You know, I already solved how we can draw a moment shear force diagram in previous example, therefore I don't want to do again. But if you have any trouble, okay, we cannot solve these, we cannot find the moment and shear force diagram. Would you like to solve me separately? Okay, I will planning to add extra video to solving to the moment and shear force diagram. But I think that you can do, because it is not complicated question to draw a moment and shear force diagram. After obtaining the moment and shear force diagrams, you can see and the maximum shear force is 20, maximum moment is 10.67. Therefore we will choose these values for calculating stresses. First of all, I want to start with the maximum bending moment. You know, we have to calculate with the section modulus. Now we will not choose the red section, therefore we have to calculate section modulus separately. If you remember, the section modulus formula is the moment of inertia time divided by C. C, you remember that C is the highest distance, the longest distance from this natural axis to point of to stresses. Therefore, in rectangular section, C is, I want to like use the, yes, here is like rectangular section, here is the natural axis, to highest distance is the top of the or bottom of the, therefore this value is 8/2 in these questions, 0.75 A. Therefore I put 0.75 A for C. Also you remember for rectangular sections, moment of inertia is B times H cubed divided by 12. I put A for B, I put B for 1.58, I forgot to write the A in here, sorry that, cube over 12. If I write these values, I obtain section modulus value with respect to the A. Okay, now I put the section requirement, and also I write the maximum moment and sigma levels. I obtain these values. Also, this value and our section modulus should be greater than this value. Then just only one unknown in here. If I take two cube square root and I obtain the A requirement, the minimum requirement A is by using this formula is 146.745 millimeter, and due to bending, the minimum A value is 1. For the A value, it should be greater than this value. Okay, then if I want to continue, So I have to also check with the shear. You remember in rectangular sections we are using in shortcut 1.5 Vmax or divided by A. If I put formulation, and also you remember I will have to convert to the again kilonewton to millimeter. 20,000 times area is rectangle, you know, width times height, and if I put A instead of I already obtained, and I find that this value is greater than our allowable stress. Therefore, it means that our section, in if I choose the A, or if I choose 146 for a minimum A value, our section will not satisfy the total allowable value. Therefore, I have to update our A value in order to satisfy the relationship. So also I require sections, I obtain the, you know, we don't know A, I have to weigh with respect to these sections. Therefore I put the A in here and max in here. Okay, sorry that I put the 1.5 in here. If I put in here 1.5, I obtain the 50,000 for area requirement. And if I continue that, you know, area is A times 1.A squared is 50,000, and I find to do requirement of A is, sorry that I think I can't, if I erase this much more better. Okay, if I find A as 170.82 times 52, this is our real smallest value of the A, not the previous value. Okay. And I want to solve one more example, and again we have a T wooden beams shown this figure and made up to sections. Also section dimension is given 30, 200, 30, 200. It's same cross sections, rectangle sections connected by nail in here. Also allowable bending stress is given 12 megapascal. Allowable shear stress is given 0.8 megapascal. Determined if they can safely support loading show, and they're asking that these sections is enough for design or not, first of all, and also specify the maximal spacing of nail needed to hold two boards between, or they are asking that space if each nail can easily safely resist to the 1.650 kilonewton in shear, as 150 meaning that resistance of shear for nail, each nail can resist 150. So in first of all I want to in second needed, first we will focus on this. First of all, we have to check our section can resist to bending or shear forces. So we have a cross-sectional dimensions, and we can also have a loading show. We can find to do maximum moment and maximum shear force and maximum moment. Then we will find to the cross-sectional properties, and we will calculate to do normal stress and shear stress, and if our section, then we will decide our section is required or not. Okay, let's continue. First of all, I have to draw a moment and shear force diagrams. You can see the maximum shear force is 1.5, maximum moment is 2. Again, if you have any trouble to draw the moment and shear force diagram, please ask me, please let me know. I will show you a small video how to draw this moment and shear force diagram. Okay, let's continue. Then I want to find two moment of inertia. You remember it's to build up sections. First of all, we don't know to centroid of natural axis. First of all, we find to the natural axis y prime. You know, already know, I think, that your centroid of the section, its formulation is y times a time divided by a. If I put to the y prime, it's the reference line. from the reference line we find to the y prime value. This is the dimensions. We converted it from millimeter to meter, and I obtained y prime is 0.1575. I think you have any trouble with that. Maybe I can explain this one more section, then you will continue. I want to explain what is the meaning of 0.1, 0.03 and 0.2. Okay, for example, in first part, and this is the second part. Okay, and A1 is equal to and 0.03 times 8 is like the dimensions is 0.03, 8 is 0.2. Therefore area is 0.3, 0.03 to these values, and these values represent this. What about the 0.1? So centroid of 2 we know in middle of this, therefore and also reference section is bottom, therefore this distance should be 0.1. I obtain from here. What about this? Again area is similar because the dimension is same, 0.03. this one is the 0.2. therefore this value is not changed, width and height. Also if I take two line between the bottom to centroid of this, 0.2 times 0.03 divided by 2, therefore I obtain 0.50. I think that there's some kind of, yeah, this is not 0.215, not this one. This is miswritten, I think that. After that we obtain these values. Okay, I want to raise, so also small help to obtain y prime value. So you remember the moment of inertia, how the calculation of this. Parallel axis theorem you already know, but I think that I can do it for you. I can use my small whiteboard in here to calculate this. Okay, and now I'm preparing my whiteboard. Okay, this one is much more better. Okay, not this one. Okay, like this. We have, you remember that moment of inertia is equal to sigma 1 equal to 1 to like number of two parts MP, like IE times YE square AY. This is the parallel axiom theory formulation. Just MP meaning that number of parts. So AY is the moment of inertia with respect to the centroid of each part. Y is the, I don't want to write the dy is much better. Dy is the distance between the centroid of the part and to centroid of the system, and AY is the area of each part. So first part, in the bottom part we have like B is equal to 0.03, H is equal to 0.2, therefore moment of inertia centroid of their axis is in B times H cube divided by 12 times, and in order to calculate the dy, how we can calculate dy? So we know our reference axis in here, and we know the distance between the reference axis to this part 0.5, 0.1, you remember, and also we already know the centroid of the system. This is the 0.1575. So I am wondering this distance. I have subtract these values. Therefore, I subtract from these values to these values 0.1 minus 0.1575 square. Okay. Times area. What is the area? Area is 0.02 times 0.2. This is the first part. And I want to continue the second part. You know, in second part is the like this. I want to add again, and width is in b is the 0.2, b times 8 cube over 12 times. Now I want to write to do there. Also we know the distance are from the reference line. You remember that this distance is 0.215. Therefore I have to write in here 0.215 minus 0.1575 square 0.03 times, okay, no, for consistency I can write like this 0.03. And after that I also add these two terms. I obtain to like this value from meter. Okay, then we already know the moment of inertia, and also we can calculate the Cmax. You know, I wanted to go back to our webcam. Okay, which one should be in Cmax? This one is the bigger and this one is the bigger distance. I think this distance is bigger, therefore, so this one is 150.75. You know, Cmax is the maximum location from the natural axis of our system. This is the 115.75. What about this distance and top of system? It's equal to 2.5 in here, like is equal to total height of system 0.23 minus 115.75. You can see this is much more smaller than the 157. I think that this one is, I think that 17 is equal to 17 like this. It should be, I can't calculate it correctly, but I think like this. And which one is the greater? I think that this one is greater, therefore I choose Cmax is like this. I took these values 115.75. Then we already know the moment of inertia and V sigma. Forgot to write, sorry, that in here I should put the C in here. Okay, after that in sigma allowable these values should be smaller than the sigma allowables. Then if I subtract, if I check, this value is 12 10 to the power 10. There we are now sorry, I think this is not which units we are using. That Newton kilometer, this should be kilopascal, and this should be yeah, they are always, we are converting to the pascal, therefore this is the megapascal. In order to convert to the pascal, we obtain the like these values. It should not 9, it should be 6. I miscalculated, sorry that. If I put in here, this value is 12 10 to the power 6. This value is 1 5 7 24 10 to the power 6. this value is greater than this value and our criteria is satisfied, therefore we have no problem for bending check. For shear check we have a Vmax. This is the unknown shape, therefore we cannot use, unfortunately, to shortcut formulations. Therefore we have to calculate to the Q. So which Q is the much more in centroid is the much more critical, therefore we calculate Q instead of this. We can use both this and this one, it doesn't matter. I think, do you remember Q is the Y times A prime. A prime is this area of this part, okay. What about the area of this one? We already know the length and cut, and therefore we obtain the Q value, okay. And Y prime is the centroid of, do you remember the Q? I think that I can use also my slideshow calculation of Q. Try to also, you already know, you should be know from chapter 7, but maybe remind you, maybe it can be helpful to remind the formulation. Okay, how we can calculate the Q? Q formulation is like this. How we can obtain Q? Q is the area moment. In formulation is Q is equal to integral 1 times A. Is Y meaning that, and like I can just distance between centroid of area of A prime to natural axis. Therefore, in our question, we have shape like this. So here our natural axis in here, and I said the most critical point is the natural axis. This we call as A prime like this. So centroid in here, therefore Y is equal to 0.5 over 2. This area is 0.3 times 0.1575. Okay, if I multiply by this, we obtain Q. Some of you may be asked that, Hocam, why we are using the up direction to calculate the Q? I can say that if you want to calculate in up direction, you will obtain same value. Why we are choosing the bottom? Because this calculation is more simple than the upside, because two parts available on the upside. Therefore, I prefer the downside to calculate Q value. Why we are choosing the natural axis? Because Q is maximum on natural axis, 0 and 0 on the top and high point. But for normal stress, the critical point is top and bottom. On natural axis, normal stress becomes 0. Okay, so I wanted to go back to the screen. So I calculate the Q, then then I will check to the two levels. You remember Vmax times Q, I forget always the formulation, sorry that, times E times T. Then I calculate to the 300 0.10 to the power 3 Pascal. It is smaller than the 800, therefore our section is satisfied. Therefore we don't have any problem to shear check. Now I want to go back to where is it? To nail space, finding the nail space. Specify the nail needed to hold 2 bars in nail can safely resist 1.5 in shear. So most of you, if your instructor show you to this check or not, but I want to remind you, I want to go back to the chapter 7 And chapter 7, where is it? Shear flow in build-up members. We calculated to Q. It's very similar to shear stress, just only thickness is not considered. If Q should be smaller than 2 V divided by S. So our formulation like this, Q should, I want to also simplify with a like question. For example, if your nail stress is 40 Newton, if I divide it by the space, this is the Q occur, it should be, you can see, 40 times 90, it should be Q requirement smaller than the Q requirement. Therefore, first of all, we find we Q values, required Q values, and then we find to the space values with respect to the nail requirement, nail strength. Okay, so I want to go back to our slide. Where is it? Here it is. So my nail stress is 1.5. We don't know the space. I put as, therefore it should be V times V max times Q times moment of inertia. So we know V max, we know Q, we know moment of inertia, we know V.5, and we subtract S. So if I go back to the formulation, so we know I put V max, I put Q, I put moment of inertia, I calculated to Q max, it should be nail allowance divided by S. I'm sorry, I write D in further, then I put to D 0.74 meter. This is the distance between the nail. So I finished to do build up. I finished to do beam design requirements. Also, I wanted to last sub-chapter in this chapter is the fully stressed beam. It is not complicated. Just I mean that in this subsection we have beams have a unique that constant cross section. We have a variable cross section. In this that we try to find to do area of 2 or any cross section dimension of 2. For example, such as height of beam with respect to the x. So we are trying to generate the formulation. This is not constant value. This is we try to find to do, for example, h value with respect to the distance. So how is it finding? For example, if we find to the Sx, you remember that S is the section modulus. You know, we already know Mx, we already know sigma allowance. So we find the Sx with respect to Mx. You can see M is not we will take to the maximum. We will take to the each location, every location we put to the Mx, and we try to generate to the S formulation, section of modulus formulation with respect to X. Okay, so I think that the question is practicing the question is much more clear. So we have to determine the shape of fully stress of beam can resist the concentrated forces in stress. In this figure you can see shape is not constant, and if beam has a rectangular cross section but height is not constant and thickness is given as a beam, and allowable stress we take is not numerical value sigma allowance, and take the height of the middle of the midpoint of the beam h0. So they are asking that the AX formula is needed. How is it find this? First of all, we try to generate the MX formulation. So this is very simple loading type, therefore we can easily generate the moment formulation by MX is P over 2 X. How is it find? Maybe if you have any trouble, okay, I will find you. And this is P over 2, and this is P over 2. If I take a cross section anywhere of the beam like this is the moment, this is P over 2, and this is X. I want to define is a 1.1. If I total M1 is equal to 0, I can easily find M is equal to P over 2 times X. This is exactly what I need. So we already know the Mx. Then we can find the Sx. Sx, you remember that Mx sigma allowance, and 2p times 2 sigma allowance. I want to write to Sx formulation. You remember the I times C. For rectangular cross sections, moment of inertia is 1 over 12 b times h is cubed. H is not constant, therefore I want to h is like the function formulation. We also I want to see is that C is the maximum distance from the top of bottom points to the natural axis. This is hx over 2. If I put values in here, and I also right side of the equation is, you remember that P times sigma allowance, and I want to see if I want to sigma h square alone. Sigma h square is hx square, hx function is 2p sigma allowable b times x. So I find the hx formula, but it depends on p and sigma allowable. If I have chance to do eliminate to do p and sigma level, yes. So I say that we know the h is maximum, or h is to h0 at midpoint L2. If I put L2, so that should be is equal to h0. So h0 is equal to 2pl over 2 sigma will be, and therefore 2pe sigma will be is equal to 2h0l. So 2p sigma will be, you remember that this value is like this. So therefore, instead of this value, I can write 2h0 square over l. Then h square is 2h0 square over lx. Is very simple formulation. Okay, this is the last example of this chapter. Again, if you have any question, please let me know. I hope you will not have any trouble to understand the questions. You remember, you can realize, I changed the slides. I tried to simplify the calculations. Also, I'm planning to add additional form in this chapter. And if you have any question, you can ask by using forum. Also, we have a classroom system. Also, you can use the classroom system to contact me. Okay, see you next time for chapter 12. See you. Bye bye.